All right. As Samit has told you, the title is Adversarial Intelligence in Natural and Artificial Systems. And my goal is to replicate that adversarial intelligence in computers, which is therefore an agenda around artificial adversarial intelligence. So to get started, to show you my agenda, let's dig into some examples of adversarial intelligence so I can tell you what I mean by that. And this is one of the best examples I have, right? Does everyone recognize Wile E. the coyote and the roadrunner? Well, these guys are adversaries, right? Why are they adversaries? Well, Wile E. wants to catch the roadrunner, and the roadrunner wants to get away. So Wile E's objective is in conflict with the roadrunner's objective. And that's one characteristic of the adversarial settings I'm interested in, right? The other thing I'm interested in that Wile E and the roadrunner do is that Wile E's behavioral repertoire, the kinds of actions Wile E takes, are asymmetric with respect to the actions that the roadrunner takes. So in this paradigm, what I can imagine, what happens is Wile E and the roadrunner engage, right? They have some sort of competition. They both have different objectives that are the opposite from one another. And because they're intelligent, right? These are really, really cool cartoon characters. They, as a result of this engagement with each other, they withdraw, and they're able to observe what happened, and they modify their strategies for competing again. And that hallmark of adversarial intelligence, the ability to learn from what happened and adapt a strategy, is also key to the adversarial settings I'm interested in. And what happens when you have two adversaries, and they're able to learn, is that they can actually ratchet up the complexity of their strategies from very simple to more complex. And that comes because they basically co-adapt to one another, right? And in real life, that escalating arms race that we can see in one episode of Wile E competing against the roadrunner, or across episodes, it plays out in the real world, with populations, right? There's populations of coyotes that evolve over time to have good strategies for catching their prey, because they act as predators. And of course, there's prey that evolve strategies in response. So there's a locked-in coevolutionary battle going on here, and evolution is responsible for the learning of these different populations. And there's different examples of evolutionary learning of adversarial adaptations. I just love to show them. So indulge me. What you see in sort of the diagonal from bottom left to top right is how evolution has helped to evolve camouflage as a defense, right? This is actually sitting in here. That's a cephalopod that is able to actually dynamically camouflage itself, and it's evolved that capability. Here's another example. But what's going on here is mimicry as a defense. This is the viceroy. The viceroy looks like the monarch. The monarchs don't taste good to predators, so therefore the predators don't eat the viceroy. And over here is a defense that's actually twofold, right? Predators from far away see the stripe, and if they don't get the message with the stripe, the skunk has its scent as well, right? And there's also been adaptations that have evolved for predation, for attackers, and these are fairly obvious, except for the one on the bottom left. Can you pick out the attacker in that picture? It's the spider that has actually evolved as a predator to be able to camouflage itself in the flower so that it can actually capture the wasp here, right? So if I'm going to replicate adversarial dynamics, that arms race between adversaries, and I want my adversaries to behave intelligently, one of my workhorses is the evolutionary algorithm, right? And I just thought I'd put it on the page to make sure we're all on the same page with it, and actually to draw some connections and connect some dots between all the work that's been going on here for the week. So in an evolutionary algorithm, we start with a population of genotypes, and they're translated to phenotypes. So they move from a representation in our algorithms, which is numeric or binary, or it looks like code perhaps, and then they are translated so that they actually have some behavior in a phenotype space. And in our algorithms, the behavior of the phenotypes is evaluated, a member of the population is given some fitness score, and when we've evaluated all the fitness scores of members of the population, we select based on the fitness, the better ones, and then we take that genotype representation in our algorithm, and we actually apply an evolutionary principle of random variation on it, right? So people here are doing code synthesis. Let's map that into this framework. What we got is a paradigm called genetic programming, and we have a population of expressions of code, right? And they're now being run. The code is executable, it's run, so we look at the behavior of that code, and we determine whether that behavior is useful against some set of input-output experiments, tests, and then we select based on the behavior how many input-output examples are correct, and we do variation on some representation. So when you saw Levi talk on the first day, Levi represented his code as trees, and he did that random variation on the tree. Right? And he still got syntactically correct code from the origin point. When you saw Kevin had, he was conducting code search, right? And you saw Sumit do that as well, right? So we choose different representations, and we have different search algorithms. But fundamental here is that we decide that we want to represent the behavior of something with code, and we're going to search for better and better pieces of code. And how we search depends on the algorithm we choose, and we also have choices with the representations, right? So what I'm doing here is I'm not really doing program synthesis, but I'm using code to express the behavior of my adversaries in their battles. So that's the evolutionary algorithm, but I'm interested in these coevolutionary arms races. So I need to model two populations that compete against each other with conflicting objectives. And to do that, basically I take two evolutionary algorithms and I couple them into one. And the way they're coupled is through this population in the middle. But what we can talk about is that coevolutionary algorithm as having two populations, one for our attackers and one for our defenders. Typically attackers are in red, defenders are in blue. And the actual population loop continues for the blue independently of the red, except for the fact that we now want to compete defenders against attackers to understand how fit they are. So what the algorithm does is it may take one defender into the competition arena, and it may then take one attacker to meet it, and it will compete them, and the result of that engagement adversarially, it gives us one point estimate of the fitness of an attacker and defender. So the algorithm can repeatedly reset the competition and take many different attackers one at a time to get an estimate of a defender's fitness, and vice versa. They can take an attacker into a ring and reset every engagement against a different defender, and now you get a better estimate of an attacker's fitness against all the defenders and vice versa, right? So at the limit, it's an n-squared evaluation for two populations.
So just for context, in the Wile E. Coyote situation, the objective, the goal is locked, and the strategies change to achieve that goal, or
Yes.
can the goal can't adapt? What Coyote can't become vicious?
Right. I'll show you three examples. We're going to do case studies today. So what's sort of so what couples them is that we get fitness information by using the other population, and we have to set up this competition ring to actually execute the defense and the attack against each other, because we want to behaviorally have that engagement. I do. But the selection and variation things are the same.
How do you determine when to stop? Like, when do you stop the algorithm?
We just put a limit on it. We can run it for a number of generations. We can run it for a number of fitness evaluations. We can run it for walk-log time. So here's where it starts to get interesting. I'm going to show you three case studies where we have an adversarial attacker-defender relationship. And I'm going to show you how we investigated the evolutionary arms race between them. And the three domains are taxation, generative adversarial networks, and cybersecurity agents. So let's do case study number one. And in this case, what we were trying to replicate was the arms race between tax avoidance and tax auditing. So that may take you by a little bit of surprise. That's not a typical thing you see in program synthesis problems, but I'm not really doing program synthesis. What I'm really studying here is adversarial behavior. So we built a system over 6 or 7 years, named Stealth. It was built by a senior member of my team and a couple students, but it also included subject matter experts from the domain of taxation. And they themselves had connections to the Internal Revenue Service where we really could talk about people who were looking at tax regs. So we had to do an awful lot of domain investigation here. And at one point, we literally sent Jacob over to Harvard Law School, and he learned about tax. So a huge amount invested in understanding taxation. And that's because tax avoidance or non-compliance is a more technical term, what's colloquially called tax cheating or scamming. It's actually a pretty costly problem to the coffers of the U.S. Revenue Service, right? And just to think about it very clearly, but simply, the government wants to tax your profits. And so one way you have of minimizing your tax, because you don't want to give the resources money and you don't want to give it to the government, is that you can inflate your losses to hide some gains, or you can hide your gains from the government, right? And because taxation should be fair, you want all those strategies to have economic substance. They have to actually be legitimate when you do this reduction in your capital gains or your inflation of your losses. And sometimes they're not legitimate, and that's what the government's after. Now, why does it happen? It happens because of the complexity of the environment in which these adversaries are working, right? It's the tax code environment, and what we want is a fair taxation system. And one of the principles in the US government taxation system is that you should never be double taxed, right? And so we have all these different financial entities in our system. We have individual taxpayers. That seems pretty obvious. That's all of us. And let me tell you, the government's not worried about all of you. They're more worried about the fact that there's corporations of different sorts legally, there's partnerships, there's trusts, and there's all these other financial entities that can buy and sell goods and that change their ownerships and that could turn a profit. And sometimes that profit is taxed at the partnership or at the corporation, but other times it's actually flowed up to an individual. And you never want that flow to result in double taxing. So that means there's an awful lot of arcane and rather complicated tax rules that can be taken advantage of. And I'm just going to show you, when we didn't know anything about taxation when we were asked to look at this problem. But what we did was we started to really understand a few of these scams. And then what we wanted to do was come up with a method that could replicate those scams. And we knew that if we could replicate those, then that method could be carried over to other regulations and other sorts of behaviors to find new and anticipate new scams that the IRS might be worried about. So here's one of the scams that we looked at. It's called IBOB. I'm not going to give you the translation, but imagine Jones has a house. He bought it for $120. So he wants to sell it to Brown, and Brown's ready to pay $200. So what should happen? When you have a house that has a basis of 120 and a fair market value of 200, and you sell it to Jones, you sell it to Brown, Jones should pay tax on that $80. So now I'm going to show you a scheme that hides the $80. All right? So what happens here is, again, we have Jones with the house, and Jones sets up a partnership called Jones Co., and he pays for his partnership share with the house. And Jones Co. sets up another partnership called New Co. and pays for its share in New Co. with the house, right? And now when the house needs to be sold, what happens is Jones sets up another partnership called Sideco. And Sideco now says, I'm going to buy New Co. from Jones Co. Right? And I'm going to pay for it with $200, right? Because that's the fair market value of the house, $200. And I'm going to promise to pay Jones Co. in the future $200. And when Jones Co. gets that $200 later in the future, it will pay taxes on it. But at the same time, because the house is now being moved over in terms of the partnership shift, the house you can actually use an adjustment in the tax code called the 743 basis adjustment, and you can adjust the basis of the house from being worth $120 to $200. And now when the house gets sold to Brown, it's worth $200 within the partnership structure. There's been no tax paid on those annuities because they haven't come in yet. And anyways, they'd be paying yourself, right? So in two ways, they're fraudulent and have no economic substance. And now when the house is sold to Brown, it was worth $200. It's sold for $200. There's no capital gains. Okay, so the networks where you see this are about, this is a small one. The IRS is faced with an uphill battle where they issue letters where they sort of say what you can and can't do. They have auditing, and they move their resources to try and audit the things they can observe. And over time, as their auditing sort of ramps up, so do the size of these networks and the quantity of them. And they're shockingly big and shockingly frequent, all from this sort of intelligence going on at the accounting side to find loopholes. And effectively, here's what's going on, is if we actually consider the top of this chart to sort of be who's in control of the system or who is being successful at their objective, because auditors have an objective that's opposite to that of tax evaders, what happens at the beginning is the IRS may set aside some of those resources to write those letters and study fraud behavior there, but they also want to audit all these transactions. But they don't have enough resources to cover everything they can observe about those transactions. But they may get their resources pinned on the right observations. And once they lock those resources into the right observations that are sort of matched to the kinds of schemes they're seeing, then they suppress the schemes, right? But what happens is over time, the schemes evolve and they move to different behavior. And under those behaviors, the observables that the auditors are trained on are no longer going to be able to catch them, right? So what happens over time is you see this swatch in who's actually ascendant, and this is our coevolutionary arms race here. It's kind of an oscillation. Steph.
Can you say something about the relative timescales of
That's
the
interesting.
adaptation? I don't know if I'd call it evolution, but the adaptation on
It's years.
party?
I mean, it's years. So,
No. Relative timescale.
okay. Of each
Like,
shifting?
are the auditors faster than the
No,
scammers?
the auditors
or
are way
vice versa?
slower than the scammers. The auditors take a long time to figure out which observables to look at.
So how do you account for that in your model?
Well, I will in my algorithm. I run my algorithm in something called lockstep, where I allow more time for evasion to occur and then less time for detection to have. So I just simply make an algorithmic change to deal with that. And what's interesting is that, right? Okay, another question? Sure.
Are these unintended consequences of broken tax code, or people are doing something illegal here?
There are unintended consequences from the point of view of the IRS who wrote the code, yes, and like it's legislated the code, and it's never sort of thrown away, just new things are put on top. And with this problem of doing fair taxation without dual taxation, there just are many, many loopholes. And often legislatively or with letters, they'll try and close a loophole, but there's another one there. So the schemes are called like boss and son of boss. And we haven't been able to, we can read about the IRS. The IRS tells us about how they've changed, but they don't tell us about how they detected them or how long it took them to do that. So there was a scheme called BOSS that they finally discovered, and it took them 6 years to get everyone to find the economic substance lacking. And then son of boss arose because they changed some loopholes, but people found other ones, and so they were caught in the same situation. And that's kind of what, this is obviously research. It's not, it did actually end up in the IRS and stuff, but really this was about saying, can we get ahead by modeling the dynamics? Thank Jacob.
What is the sort of penalty when companies are caught doing?
You can go to jail. So for son of boss and boss, the accountants went to jail. And KPMG paid millions of dollars in fines. So they actually, for boss, they caught the accounting firms, and then they also caught some of the perpetrators. But they go after some, but they don't have the resources to go after everyone, right? And of course, the next era of this, just as we finished the project, was the Panama Papers, and it was all being done offshore. So there, it's a little bit more complicated because it's about offshoring and free tax zones. Question, Ida.
What's the fitness function, and is the fitness landscape dynamic or static? Because when the laws change or some policies change.
So I'm going to have the regulations stay constant, and I'm going to show you the fitness function in a second. I'm going to go through the whole thing. I'm going to step through it.
Yeah. So you have the government and you have the scammers, and I wonder about the public in all of that. How do the changes in the code to suppress the scammers affect other people?
They must. I mean, but I can only tell you about reading it in the paper and reading it on the internet. So, they make examples of people, right? I mean, but I don't know. That's out of my realm of modeling. But it's absolutely true that good enforcement actually leads to people actually following the rules. Poor enforcement leads to worse stuff. So right now we're working with, the project went into stasis and has just all of a sudden been revived, and we're looking at using new methods that might involve language models and things. We're looking at like a country like Colombia, where there's such a perception that the revenue code doesn't serve anyone fairly, that it encourages other behaviors.
But I guess my question is, in designing a certain fitness function or certain actions, that is going to improve the situation against the scammers, you might incur more cost to the public that it is not worth it. Maybe.
I don't model that. I just can't. I can't model all those variables. And so you'll see this is an abstraction of the situation, but absolutely has other implications. Yeah. So say I want to model this coevolutionary arms race between that. The first thing I need to be able to do is have a space where taxpayers can act and behave, right? And that's the space of transactions and sequences of their financial transactions over these entities and assets and payments, right? And to do that, what I do is I set up a grammar in that space. And in my software, I make sure that I have implementations of the actions and the objects within the actions of this space, right? So this grammar is essentially a representation of a domain-specific language, like you have. And the domain-specific language is the language which we're concerned about for tax schemes like IBOB, right? So it's narrow, right? But it involves allowing any individual in a population of evaders, they may be lousy at it, to be able to create these partnerships, sell these assets in return for things. And every time, so let me just talk about this. So my evolutionary algorithm has to represent a phenotype, which is a transaction sequence that's going to be derived from here, right? And so I have a genotype, which is a vector of integers, and I use the integers plus that start symbol transactions to count off my choices and generate a sequence from this grammar, right? But I can take this integer sequence and I can modify it, and by modifying that, I get a different transaction sequence. So I'm evolving and doing variation in the space of integers, but I'm actually operating and selecting and looking at the behavior in the space of transaction sequences. And I have this all implemented so that when a transaction sequence for a vector of integers comes along, I can set up a portfolio, and then these transaction sequence takes place over the portfolio. And as the assets are changed and the partnerships are bought and sold, I can even, what I have to do next is, so this network is unfolding. What I have to do at the same time is represent the tax regulations and make sure that as you walk through the sequence, if any action in the sequence triggers a tax regulation that changes the basis, we want to run it. So that's actually a little complicated. We had to read all these sections of law, and then they're all linked, and so we found a little small network that we could represent in this problem space. And we created, just in software, decision trees that reflected sort of the choices that you were being given by proceeding through these networks of tax regulations to change the basis or the fair market value of your asset. So with these, think about it now. I've just described to you a behavioral space of transaction sequences that a population of potential evaders has. When that transaction sequence is actually executed, some of these tax regulations are going to get triggered. At the end of some sequence, we'll know whether an object, like the house, has had its fair market value hidden or not, right? So now what I should be able to do is run one evolutionary algorithm and find a scheme, right? Because some of those transaction sequences are not actually saving anything, right? They're just random, and some will do that on tax. So here's my population of genotypes, which are vectors, and they're tax evaders. I decode them into a transaction sequence. When that transaction sequence triggers a basis adjustment, my code takes care of it, and I see if there's a tax gain. That's how fit you are. You're fit if you actually you managed to actually hide your taxes, right? A minimal tax gain, right? And amongst those better strategies, I do a selection and I randomly vary those vectors and I get a new generation. And if I run that, here's the picture of that running, right? What I've got here is over time, my genetic algorithm is running over time, generation at a time. It has some population size. I'm not telling you that, that's not important. But initially, nobody in the population of evaders is very good at evading tax. But that's the fitness selection variable. So over time, we see evolutionary adaptations, and IBOB emerges. And I've set this up so that IBOB is possible, but many other things are possible as well. So we've done search on the space of code and transaction sequence as we execute them to come up with that scheme. And then, of course, there's nothing to stop that scheme from now proliferating, right? Because I don't have any auditors or anything. And so now the best individual in the population and all the members of the population start doing that, right? So I need to build the other side of my system out. I need to represent that auditing. So it goes back to those notion I introduced of there being observables over transactions and the auditors having some fixed number of resources. And what we did was we went in and we extracted the observables for this network of tax regulations. And then we could record when a transaction sequence was executed, we could record what was observed for each of those observables. And then each auditor has a vector, and it gets to put some portion of its resources on those observables, on one of those observables, across those observables, right? So think about it. If I have infinite resources as an auditor, I'm going to put the same number of resources on all those observables. But if you give me less than there are the number of observables, I gotta pay attention. And think of those weights on those observables as actually having a magnitude, and that means that I can sum the weights, the weighted observables to get a score for an auditor. And so if an auditor sees a transaction sequence of an evader and he gives it an audit score, right? If the audit score is high, that would say, I think you're evading, but I may be a really crappy auditor, right? And I might also miss something. I may say, well, that's a low audit score to an evader that's actually evading lots. And eventually we want that auditor population, something to emerge that puts the weights on the right observables with its resource budget in order to capture and lock into the observables that match the best evaders, right? And so to set this up, we have a fitness function. Who asked about the fitness function? Yeah, so I'm not going to give you the numbers, but an auditor is going to be fit if they assign a high audit score to a highly non-compliant evader. So that means I managed to hide a lot of money as an evader. And an evader is fit if they receive a low audit score but are highly non-compliant. Because we don't want to waste our audit resources on a very small amount of tax savings. We want to get the big guys, right? We want to get the big fish. So the corollary is that an auditor is fit if they assign a low audit score to a compliant transaction sequence, and an evader is not very fit if they're compliant. Right, so all those things are going on, and this is the only chart I'm going to show the dynamics. But let me walk you through it. Again, we run one round of the system with now a population of potential evaders who are trying to evolve to good strategies of evasion, and a population of auditors who are trying to move their resources around by weighting the observables they think are important for the evasion. Right? And this is going to run for a number of generations, and I'm showing you the auditors and the evaders here. So along this axis here, this y-axis on the right, I'm plotting the fitness of an evader with respect to it trying to evade, right? So it's in black, it's shown here in black, it's oscillating here. And rather than show you, the best way to show the auditors is we took 4 auditing observables, and we gave the auditors only the chance to pick at most 3 of them, right? And each one of those observables we've coded in a color, and how much weight is on them is by how long that bar is for that color in that row, right? So initially, you can see that the best auditor, and all I'm showing you here is the best auditor and the best evader. Initially, we get a random evader that's actually pretty good, and the auditors with these weights on, the best auditor with these weights is not sufficient to sort of suppress it. But what you see here is by just the changing colors, the auditors are shifting weight, and now the fitness of the scheme goes down as more audit weights are shifted towards to lock into the observables that the evader is using. And that's what pushes this evader fitness down. And at this point here, the evaders have to come up with a strategy that doesn't match the auditor's weights on the observables, right? And that's what they do. And actually, I asked myself this morning, are these different schemes that are emerging each time? And the way you can tell they are is because the auditing response is different each time, right? And it would have to be, the auditing response that drives them down has to be different depending on that. So this shows the coevolution of the system dynamically. Levi. And then Martha.
When computing the fitness function, you have to pair it up with other individuals in the population.
To get an estimate.
Do you do it randomly? Do you just for one? Do you sample?
We had very small populations here. It's not a big search space. I mean, it was more the principle than the repetitive inside. So we probably did all versus all. So that's an n squared population size, yeah. So lots of publications on this over the course of 6 years. And actually, the most gratifying part of it, though, was that to learn back that this had actually helped the Internal Revenue Service. So what we did was we turned them from looking for needles in haystacks to actually hunting down things. And they could either hunt them down and anticipate them ahead of time, or they could hunt them down later. So everyone,
You
yeah.
share these new schemes with the IRS?
I never produced, well, we produced one new scheme so we kind of went back in the code, and we were trying to replicate IBOB, and then we found another variation of IBOB, and we showed it to them, and they were like, yeah, we knew about that when we closed it up. It was kind of like, I mean, the IRS wouldn't talk to us for like a year and a half or so. Our intermediaries dealt with us and taught us a lot of things, and eventually we had some credibility, but I think you want to think about this as an approach, right, where you change things from deduction to search. And then you have to do all these hard things like come up with representations, AI representations for the different elements. Steph. Oh, wait, I owe Martha. I owe Martha because she's had her hand up. Sorry, Steph.
You maybe just answered this, but so in a real population, obviously most people are actually just compliant, right? So does that fact does that play into your results at all?
Well, we allow for compliancy and we allow for it to arise, but because we're trying to find good auditors and we're trying to understand what may happen, what the discovery of new schemes in that population of possible schemes, we emphasize those rather than the malign the benign things. Right? Our fitness function kind of does that, right? We don't really want to find the ones that work, where everyone's compliant. The IRS is less interested. They want to know what the observables, where they should put their weights on the observables.
Yeah. So you're searching for the schemes. Yeah.
Yes, and it's way more complicated than this for them. Let me tell you, way more complicated than this for them. But I would not claim to be. I mean, the ways in which people evade are quite interesting and high volume, and big size, big scale.
I've got a couple questions, but anyway, on this all versus all thing, I mean, are your populations like 5 or?
Oh, no, they're like 50.
50, okay. And then
It doesn't take long to run.
presumably, the fitness for the evader is predicated on the best of the auditors, right? It only takes one auditor to find an evader.
Well, that's what's interesting.
And vice versa.
Do you want to be?
Anyway, like I'm just exactly how do you do the scoring? And then my second observation is 3 observables from what little I know about kind of forensics and accounting.
Yeah, no,
seems
we're
like
close.
it's very, very minimal.
Right, no. In reality, it's
So,
thousands.
like-
Yeah. No, I'm not trying to.
How hard is it to scale it up? And
I don't know, because so when the problem was first given to us, okay, so 2 questions. First is, what makes someone fit? Is it your best performance against the weakest auditor, or if you're an evader, or is it your performance against the strongest auditor, or is it your performance on average? We do all sorts of things like that, and especially when we do cyber, we pay a lot of attention to different runs with different criteria for how you define fitness. Because I think
it's asymmetric between the evader and the auditor. 'Cause
It can,
the
and we
auditor,
often set it up
I
to be
mean,
reciprocal.
The auditor, you only need the best one.
Yes, you could have a different objective for both of them, right? I mean, you could definitely have a different way of calculating the fitness for an auditor versus the fitness for an evader. Absolutely, yeah.
Maybe I missed this, but is there learning on the auditor side such that the same schemes aren't reemerging after?
Well, the
6 months
auditor is
to like-
moving its weights around on the resources, on the observables with its resources. So it's possible that the system oscillates, but the way we know it's not actually here just is because we can see where the auditor is putting its weights, and it's in order to drive the schemes down. Yeah, it's kind of, yeah. And like, it's really complicated once you start running them, even like in a toy situation where I've got 50 and small numbers of observables. I never actually think that the IRS is running a coevolutionary algorithm. I think they're more just understanding how they can represent schemes and search for them. And I just don't know to what scale it's being done. As you asked the question here.
Yeah, so from your definition of the fitness function, there is no accounting for false positives, correct?
There is, because you get penalized if you're an auditor, you get penalized if you say your score is high on somebody whose evasion is low. You'll get a low fitness.
And that is not taking the evolution of those strategies into account.
No, it's just on that strategy. Yeah, yeah. So I'm going to move on to a second case study, and I think the way I would contrast these is, boy, it's hard to work in domains where you don't know very much, like taxation, and it was just like a really welcome occurrence that within computer science and machine learning, there's actually also an adversarial paradigm that's been set up, and that's the generative adversarial network. I'm going to talk to you about a system we call Lippinzaner. This is named after the stallions that work in formation in space. And we tried to improve the efficiency and robustness of training GANs with spatial coevolution. And so the first thing for me to do is to tell you what a GAN is, just to review it for everyone. So the problem we're trying to solve is that there's some latent distribution. It's hidden from us, and we have samples of it. And what we'd like to learn is a model of that distribution that's hidden. And we're going to learn that model. We're going to learn that in this model G. And to actually train this model G to come up with the latent distribution, what we're going to do is also have a second model, a discriminator. And G is going to take random samples and random inputs, and you'll run them through G, and it will create a sample. So here I've got a distribution of horses. There's real pictures of horses, and we want G to generate pictures of horses that are fake, that it's never seen before, but that would legitimately come from that hidden distribution, right? So G's got fake samples, and there's some real samples here. We set up G and D to be competitive, right? They both start at random, and they don't know very much. But what D's trying to do is to distinguish real data from fake data. And when it does it well, it gets a reward. And when it does it poorly, it needs to be trained with gradient descent to improve its parameters. And what G's trying to do is send fake samples to the discriminator and fool it, right? So G gets positive feedback when D says, oh, I think that comes from the real distribution, but it gets negative feedback when the discriminator finds the fake sample, right? And with this min-max optimization and this adversarial dynamic, what we hope is the system is going to start from scratch, but eventually co-evolve to, not co-evolve, but co-adapt to a generator that's so strong that the best the discriminator can do is just flip a coin to guess whether it's a real sample or a fake sample, right? But it turns out to be pretty problematic to train these. They can just not converge. The training may not converge because the parameters are oscillating and they destabilize. You may have several modes in that hidden distribution, and the generator can only come up with, given the samples, it's only going to come up with some of the modes. And sometimes, the discriminator is just so good that the generator doesn't have a gradient. And so you meet people who love this paradigm and they want to train generative models this way, but they just have a really hard time. What occurred to us was that perhaps coevolutionary approach in tandem with the GAN approach, we could come up with something more robust because evolution tends to evolve robust solutions, right? So what we did, this is what happens normally, right? We take a GAN and we generate a discriminator, we try and train them, and then we start again, and we start again, and we start again. So we're doing many things serially. So instead what you could do, and the first thing we tried was we said, well, let's have a population of generators population of discriminators. That's my attackers and defenders. And I'll, again, take one generator out, try it against all these discriminators, come up with a fitness value with it. Take a discriminator out, try it against all these generators, come up with a fitness value, do that for everyone, and just run this through my evolutionary loop where I have a population of generators and discriminators. And then you sort of have to also decide how you're going to change the weights. When things have, you have to do variation on these neural networks. And so you have two choices. You could use an evolutionary algorithm to find the weights. That would be terribly inefficient because evolutionary algorithms aren't very good in real space. Or you can use gradient descent, right? We actually, just to prove a principle, did it all evolutionarily the first time with small populations. And we showed that, while we got these pathologies, they were only occurring pairwise, but because you were being evaluated against sort of, a larger set, you got a more robust estimate of a generator and a discriminator, and you could more reliably find a solution. So that sort of was interesting, but I think what's much more interesting was us thinking about the problem that these are n-squared complexity. And how are we going to get away with, this is fairly expensive. So what we did was we mapped these populations to a two-dimensional Cartesian grid with cells, right? And so at each cell of this 2D array, we put a generator and a discriminator. So now you can see your generator population across this cell, and you can see your discriminator population across this cell. But if you're in any one cell, it considers itself the center of the universe, and it has a neighborhood, right? North, south, east, and west. It has neighbors. And it can collect the generator and discriminator at those cells, right? And it can now run a 5-way evolutionary algorithm to select the best. Just run them with each other, pair them up and test them, and just see what the best amongst this group of 5, what is the best generator and what is the best discriminator. And once you select those, so you've done a little evolutionary algorithm with evolutionary selection, then you take the generator you've selected for its good behavior, and you take one of the other discriminators and train with gradient descent. And vice versa for the discriminator, you pick a generator from the population of 5, and you train with gradient descent. And now you update it, and you have a new generator and discriminator here. Okay, that looks like a 5. What's powerful here is that these neighborhoods across the cell, they overlap, right? So I may be the center of the universe, but I am actually the southmost neighbor of the cell up here. I'm the northmost neighbor of the cell down here, right? And to the left and the right, I'm involved in 5 different of these communities. And by me updating, and every generation this update happening, when I collect the neighbors for the next run of my generation, they're updated. So what I've effectively got is a signaling system across the spatial grid by the updates. And it turns out that gives you a lot of diversity, and it's the diversity that populations offer that helps you get out of these evolutionary pathologies. So we might even see here a pathology arise, but then it's actually squashed out, right? Because the neighborhoods take care of it with the communication. I mean, you can do I can't say more about just how robust evolution is and spatial evolution is to help you with these things. And it comes from heterogeneity, right? So you can do all sorts of, add all sorts of things to the algorithm. We did. We can make every cell slightly different. It might have a different loss function, right? It might have a different network architecture. And the more we make the cell, the array diverse, the better and more efficient the evolutionary, the learning scales. We can look into that signaling and solutions, and we can ablate to sort of see what parts of our algorithm, and I've left out parts of the algorithm, but we can look at what's useful. And actually, in a very positive note, you can take the same spatial mapping of populations with the 2 populations overlaid, and you can actually do autoencoding, and now you've got cooperation, the coevolution of cooperation, and gradient and evolutionary work. At the back, David. Question over hand.
So interesting idea. You're looking there essentially at planar graphs, 2-dimensional planar graphs, to define your.
We also did it linearly. We also did it with other.
Well, I was wondering, do you do high-dimensional ones? Because in terms of signal, you're going to get much faster signal propagation across your population.
It's not clear to me how fast you want the signals to go, but yes, I mean, we definitely. Yeah, let me get to that. That's great. I mean, I think there was all sorts of questions to ask.
But that should be able to actually mathematically model that.
Yeah, well, I would have to say that we were computationally starved. It's a big deal to actually put a lot of generators and discriminators, neural networks at these cells. Probably the largest study we did was like 16 by 16 in a grid, and that was at like a supercomputer at ONRL. But otherwise, we were running fairly small population sizes, grids of like 4 by 4. But we got the resilience, we got better convergence and improved convergence. And it really does scale. It's actually it can be totally asynchronous, the parallelism. So you can, you run these things in parallel. And that's a huge win. And if you actually start picking ensembles as opposed to just a single one, you even get robustness in the solution.
So what were some applications for which you got the best gains?
Oh, we were using, we did image processing, MNIST, and the bigger one, CFAR. Yeah, the digits and then the images. And then we also did one where we looked at COVID lung scans. And we did, so here's another idea that we had, and we used it. We called it data dieting. Normally you train these systems on huge amounts of data. Well, we took the data and we distributed it across the grid. So every cell just had a portion of the data, but it just learned to do well with that portion of the data. But because it was communicating its abilities on that data with its neighbors, then we actually could effectively use far less data in the gradient descent. That was actually another big win, was the data distribution. And the actual changing all the loss functions, changing the network architectures, again, that diversity allows you to find a really effective solution amongst a whole group. Yeah. So where am I for time? Oh, I'm late. Okay. Another adversarial setting is in cyberspace, where we have cyber networks that are under attack by threat actors and defenders, and we've built some systems there. There's our threat actor in red and our defender in blue, and there truly is arms races here. We see this is a report from Akamai. I'm talking about the evolution of bots for DDoS attacks. And so by this time, after stealth, actually, but before we did Lipinzaner, we sort of understood that we had a framework where we could define a predator or an attacker and a defender, so denial of service and a peer-to-peer network that needed to be defended from that, or a reconnaissance scan stage of a campaign, and a deceptive overlay on a software-defined network. And we could sort of use a framework of this coevolutionary algorithm where we would push into it for every new use case. We would have to define that grammar I gave you and parameters of the algorithm down here. And then we would develop, in this fitness environment, this competition environment, we had to say what the threat was, the threat environment, and we had to give objectives to these two pieces. And the objectives could differ, right? So we were able to do that 2 or 3 times. But I wanted to go back before I close and sort of talk about this part of adversarial intelligence, right? Like it's the use of tools, it's planning, it's sequential decision making, right? It's really where we want adversaries who behave as agents, right? Not necessarily the agency given to a strategy, right? So of course my sequences, I execute them, that's all good, but imagine that I wanted to have an agent. And where that comes in really handy is, when you're trying to solve these very sophisticated campaigns you get on networks, a threat actor is planning, is actually going out and consulting all of its text-based information and its code bases. It's using scripts and exploits to sort of hide and be deceptive and make decisions on the fly. And so we didn't really have that kind of agent in our coevolutionary systems. So we took a start, and it happens again on the defensive side, right? A defensive system in a cyber, all these events happen, and then they get sort of logged, and someone triages the logs and throws alerts if the logs look scary, and then the triaged alerts then sort of have to be classified to see whether there's a good or a malicious event happening on your system, and then a response happens. But sort of at a longer time scale, you sort of do more forensics and you figure out, well, who did this to us, and how did they do it? So we've been doing this in a number of ways, but the way I want to show you about is where we set up a pen testing environment. So penetration testing is just like you have a network and you want to subject it to attacks to see whether you have a good defense. So the good guys are posing as the bad guys, right? And so what we do is we set up a network here, right? And it's a network on a container. So in this containerized system, we literally have VMs running, and they have a command terminal. And we assume that an agent has already penetrated the system. and they now want to, from a terminal, they have access to a terminal and a user account on the network. What this agent now has to do is plan a multi-step campaign forward. And that campaign would be sort of first reconnaissance around the network, and then figuring out where vulnerabilities are, and launching a series of exploits that would allow it to sort of exfiltrate data or maybe unleash some ransomware on you or something like that, right? And so we want this agent to be able to do that. And we want this agent to do that in the space of being like they're at the terminal, like a threat actor would be, which is a fairly big buy, because up until then we kind of had abstracted the behavior of our threat actors and our defenders. And now we really want to, on the other side, have this network have logs, right? And from the logs, we want to institute all the Suricata and the different metrics for alerts. And we'd like to now use an LLM agent there, or maybe more of them. And they're going to provide the defense against the system. But the system is now totally operating in the actual real space. It's like a sandbox, right? But it's a very real, this is actually a huge step for me, because up to then I was modeling networks. I was simulating them and emulating them in a fairly nice way, but this is the real deal, right? And so we give the agent different tools. These are sort of known pen testing tools, and we can set up vulnerabilities here, and we can basically come up with like an LLM-based architecture for these agents. And so the first one we did sort of used a sequential, just looked at sequential decision making. We used these plan, act, report loops that people were using for robotics, and we melded them with like state machines that reflected the states of campaigns. And we could get sort of a script kiddie, which is sort of a very basic, it's an attacker, but it's a fairly weak one. But when we want to actually make our agents smarter, we're going to have to use sort of classical AI and the LLMs together, because we want to get planning, but we need to, and we're going to read lots of information on the web about what these agents need to know. And we want to sort of make it so that on this side, they can at least plan. And then that agent now has to learn, how are you going to make it learn, right? You have to come up with a representation space here. The agent has to not execute over the course of, like, the LLMs take forever, so there's a lot of challenges, but we're going to hybridize, like you saw yesterday, Swarat talked about, we've hybridized LLMs and evolutionary algorithms so that we can, and even use reinforcement learning as well, with a much smarter agent in a much more real environment. So that's the goal. The vision is to have, agents learning in a real environment, doing things at all sorts of levels, right? So at one level, an agent is literally has to generate executable commands in the Linux shell and in Bash. At another level, it has to be able to find vulnerabilities and choose exploits. And at another level, it has to plan how to be deceptive and stuff. And so we're trying to design that agent at all those different levels and eventually put them together and to see if we can't also do some learning from the experience. And that's it. Thank you.